Ah, Taylor series. The bane of every Calc BC student. I think they're kind of like E. Remember back in pre-calc when you hated E and thought that it stood for evil? It must have been invented by your pre-calc teacher as a novel way to punish the students for misbehaving, you thought. After learning calculus, however, you now know that E stands for easy. As an example, let's try taking the derivative of e to the x. Boom, done. Did you see that? Let's do it again. Actually, let's do it 1,000 times. Bam, there we go. It is the easiest thing you'll ever come across in calculus. I will get you to like Taylor series in the next couple of minutes, or barring that, at least give you a healthier appreciation of what they do. Alright, we'll start off with the most important question that your textbook doesn't address. Why do we need to know Taylor series anyways? Well, some functions are just plain disgusting, right? Let's make a most wanted list of functions. First, we have 1 over 1 minus x. Do you see how disgusting that is? I wouldn't want to take the integral of that. We all hate trig, right? Let's get some trig on this list. Alright, I know e to the x is pretty clean, but let's have it up on the list just for funsies. Finally, ln of 1 plus x. You can't even take the integral of this function normally with techniques that we learn in BC. That's how disgusting that is. We need to burn these functions, except for e to the x of course, in a bonfire and have them removed from calculus permanently. Polynomials are just so much more cleaner with their power rules. What if I told you there was a secret way we could convert all of these functions and more into polynomials? The magic tool is, drumroll please, Taylor series. So, how do they work? On a high level, you're extracting derivative information from a single point to approximate the function. We'll start by taking derivatives of a polynomial and seeing what happens. Given an arbitrary third-order polynomial, f of x equals a plus bx plus cx squared plus dx cubed, plugging in 0 to this function will give you the y-intercept, or the value at x equals 0 of the zeroth derivative of the function. Notice how all values with an x in it become 0 when we plug in 0. Therefore, in this case, plugging in 0 will give you a. Changing the value of a will therefore change the y-intercept of the function. This property is very important in the process of constructing our approximation of an arbitrary function. So, let's take the derivative of this polynomial. The first value drops out, and this is what we get. Plugging in 0 to this function will give you b. If we change the value of b, we will change the value of the first derivative only at x equals 0. Let's take another derivative. Now, the constant b drops out. Plugging in 0 will give you 2c. Perhaps you're starting to see a pattern at this point. We'll take one last derivative. The term with constant c drops out. Plugging in 0 now will give you 6d. The variables a, b, c, and d control the 0th, first, second, and third derivatives independently at x equals 0. If we change these to match the 0th, first, second, and third derivatives of a specific function, we can approximate it very well. Do you notice something about the coefficients at this point? The coefficient is the factorial of the power of x on the original function. Why is this the case? Well, taking derivatives over and over again quite naturally introduces factorials. As each power gets multiplied down and decreased by 1, you can see how the exponents multiply to get factorials in the coefficient. The coefficient on the bottom term is literally obtained by multiplying 5 by 4 by 3 by 2 by 1. Alright, now for a real-world function you might encounter, sine of x. Let's think through how you would construct a third-order approximation, that is, an approximation with a third-order polynomial around x equals 0. First, you'll have your function, sine of x. Next, we take a derivative to get cosine of x. We will then take the derivative 2 more times since we're looking for a third-order polynomial. Now, we plug in the value 0 to the function. Sine of 0 equals 0, cosine of 0 equals 1, negative sine of 0 equals 0, and negative cosine of 0 equals negative 1. Some of you are going to get on my case about the 0 not being negative, even though the concept of negative 0 makes no sense at all. You know what? Fine. Have the negative on the 0. We'll now plug these values into a polynomial. We'll also need to divide by the factorial of the original coefficient, remembering that 0 factorial is equal to 1. Why divide by the factorial? Remember, using the power rule over and over again introduces factorials into the coefficient, and we need to account for that in our approximation. The values with the coefficient of 0 now drop out. After simplifying, we have a third-order polynomial approximation for the function sine of x. How good is this approximation? Very, at least for small values of x. Here's a graph showing sine of x and the polynomial we just generated. At x equals 0.1, the error is off by less than 1/1000th of 1%. Even as far out as x equals negative 0.2, the percent error is within 5%. Not bad for a lazy approximation. If we wanted to make this approximation better, we could add more terms by taking the derivatives more times. Adding infinitely many terms will give you the exact value and is one way to calculate sine of x. Let's revisit that most wanted list of functions again. Now, I'm not going to go into the math for all these functions. It's pretty involved and I honestly don't feel like working through it. I'm sure your calculus teacher would be very happy to go over the math with you if you'd like. But here's the results of working through the math. Look how beautiful that middle column looks. I could stare at it all day long. You might be wondering at this point what the weird column on the right means. Interval of convergence? Certainly sounds like math gibberish to me. Let me explain. We've established that you're extracting derivative information at a point with Taylor series. Sometimes, like in the case of 1/1 minus x, the derivative information just doesn't propagate that far. No matter how many terms you add on, the Taylor series will only be a good approximation between -1 and 1. Contrast this with a function like sine of x. Notice how adding more terms increases the number of values that can be approximated, since its interval of convergence is from -infinity to infinity. Essentially, the Taylor series can approximate the series for all real numbers in this case. Think of interval of convergence like, if I add infinitely many terms, how many values can I calculate? As a side note, you might hear your calculus teacher refer to MacLaurin series. These are just Taylor series centered at x equals 0. Taylor approximations are so accurate that they can help you avoid the dreaded trig functions and maybe even some advanced integration techniques. Let's say that your calculus teacher asks you to take the definite integral from 0 to 0.25 of 3x times sine of x, but you really don't feel like doing integration by parts or voodoo. You also know that your calculus teacher only requires answers to be precise to 3 significant figures. Instead of actually doing voodoo, you can substitute the approximation we derived for sine of x earlier in for sine of x. You'll get 3x times x minus x cubed over 6, which simplifies to this. You can easily take the antiderivative of this function and get this, and then get the final answer of 0.015527. The real answer you get by doing voodoo is 0.015528. Both of these answers round to 0.0155, so if your calculus teacher only requires 3 significant figures to be correct, you're good to go. I hope I was able to give you a healthier appreciation of Taylor series. Approximations provided by Taylor series can help simplify almost every calculation in a pinch. Just don't tell your calculus teacher that you're using them to approximate definite integrals of functions that you're too lazy to figure out. Otherwise, they might just give you a problem that you can't solve. Lagrange error. Wait, you didn't hear me say Lagrange error, right? I was worried the cough kind of covered it up.